Hello students, today we are going to discuss kinetic theory of gases, which is the last part of our series States of Matter. It will allow us to account for the behavior of ideal gases and, by making a few other assumptions, the properties of real gases as well. Kinetic theory or the kinetic molecular theory of gas is based on the assumptions that a gas is composed of large number of tiny spherical particles, which we know are molecules, with non-zero mass. Then the volume of an individual particle is negligible as compared to the volume of the container. That is, the average distance separating the gas particles from the walls of the container and from each other is very large. They are in constant random motion and collide elastically with the walls of the container and with each other. By elastic collision, we mean that there is no net gain or loss of kinetic energy in the collision. The time taken in a collision is negligible as compared to the time between two successive collisions. Except collision, there is no interaction between the particles, that is, they move independently of each other, and no force of attraction or repulsion acts between them. At any given instant, there is a wide range of speeds and kinetic energies of the particles, but the average kinetic energy of all the particles depends only on the absolute temperature of the system. Now we will go through the various applications of kinetic theory one by one. The first one is the pressure of an ideal gas. As per the kinetic theory, the pressure of an ideal gas, P, is given by nmv squared divided by 3. This equation says that the pressure capital P depends on capital N, that is the number of molecules per unit volume of the gas, on their mass small n, and on the mean square speed v square. Now suppose the molecules were not all of the same mass. If we had two types of molecules, say A and B, the pressure would be due to both of them bombarding the walls, and therefore total pressure will be equal to NAMA V square A divided by 3 plus NBMB V square B divided by 3, which is easier to write as P total equals PA plus PB. This is one way of writing Dalton's law of partial pressures. In words, we can say that the total pressure of a mixture of gases is the sum of the pressures that each gas would have if it were on its own. This is Dalton's law. Strictly, the law is only valid for ideal gases. Real gases do not obey the law perfectly. Another important result from kinetic theory is the average kinetic energy of a molecule, which in an ideal gas is given by half mv square is equal to 3 by 2 kT, where K is the Boltzmann constant of value 1.38 into 10 raised to minus 23 joules per Kelvin. The value of Boltzmann constant multiplied by the Avogadro constant, that is L, is the same as the gas constant R. So we can write R is equal to capital L into small k, which is the value 8.314 joule per Kelvin per mole. The importance of the equation for the average kinetic energy of gas molecules is its link with the temperature of the gas. As you can see, 3 kT divided by 2, where T stands for the absolute temperature. The factor 3 makes its appearance in the equation owing to the three directions in which a molecule can move. If it could only move in one direction, its average kinetic energy would be kT by 2. Let's take an example. We have to find the temperature at which the root mean velocity of nitrogen will be twice its value at 273 Kelvin. Now we know that half mv square is equal to 3 by 2 kT, or V, that is the root mean square velocity, is proportional to under root T, where T is the temperature. So we can write V2 upon V1 is equal to under root T2 upon T1. Now it's given to us in the question that V1 is equal to V. If we assume that, then V2 is equal to 2V, that is twice of V1, and T1 is equal to 273 Kelvin. So on substituting the values in this equation, we can write 2V upon V is equal to T2 upon 273 raised to 1 by 2, or T2 is equal to 2 square into 273, that is 2 square is 4. So on solving this we get 1092 Kelvin. This is our final answer.